post a thing in the chat.
Oh, okay.
So it's on the bottom left of the bottom.
Yeah, it's recording now, so it's good.
Oh,
Oh, nice.
okay. Recording?
Yeah.
I see. All right.
Suck.
I guess I will begin. Okay. Yeah, thanks everyone for coming. Today's lesson is going to be Introduction to Controller Area Network, or CAN. Probably around like 20 minutes. I don't think this will be very long. And yeah, it's to give you guys a high-level look at CAN in general. So that's the first thing I'm going to talk about. And then I'm going to talk about the CAN frame, which is the more on the technical kind of embedded side of how CAN works. And then finally, I'm going to talk about how we're going to use it in our Team Phantom car. So what is CAN? Again, CAN stands for Controller Area Network. And basically, it's the major communication system for the entire car. And what it does is it connects every major component or node through this network. For example, in a normal car, you have your ECU, your engine control. You could have sensors on your gas tank, your tire pressure. I think in a normal car, there's about 70 to 80 different nodes that are usually connected. In our car, we only have three, which is the VCU, the BMS, and the dashboard. And yeah, it's just a large network to connect all of our systems so they can communicate. On the hardware side, so the physical components, usually you'll see CAN represented as twisted differential pairs. Can you see my mouse if I do this?
Yep.
Okay. So on the bottom, you can see that they're called CAN high and CAN low. CAN low is 1.5 volts to 2.5 volts, while CAN high is 2.5 to 3.5 volts. And CAN low you can think of as your normal digital signal of zeros and ones. And CAN high is the same signal, but it's inverted. So you just flip it upside down. And the reason that CAN uses two signals instead of one signal like a normal communication protocol is for redundancy and to eliminate error through any kind of interference, mainly like mechanical interference. Sorry, magnetic interference. And we also tend to twist the two wires together just so then they're physically closer and attached together so that there's less interference. And normally on either ends of the whole network, we'll have 120 ohm resistors just to signify the end of the network. So in the first diagram, you will see that we have 4 controllers or 4 nodes connected to the whole system. And the second one, shows how they can interact. So for example, on the second one, we have our node 1 or ECU1 that's preparing and sending its signal. And it's intended for ECU2. So ECU2 sees that, and it accepts it, it checks it, and then it receives it. And then ECU3, which doesn't care about the signal, will just ignore the message because it's not the intended receiver. Are there any questions for this slide?
Yeah, question.
Yeah.
So what's up with the 120 ohm resistor? I know it signals the end of the bus, but how does it do that? How is it smart enough to do that? I don't get it.
I'm actually not sure. I just know that 120 is an industry standard that they use to connect it together or tie it together. Because technically you can place these anywhere, but you just need to have 2 of them. Yeah.
Okay. But and the configuration must always be like a bus, like this line. I know there's like star configurations and circular ones, but CAN always is this bus.
Sorry, it's really hard to hear you. Are you far from your microphone? Hello?
Hello, I'm trying again. Can you hear me now?
Oh yeah, much better.
Okay, sorry. Yeah. The configuration is this. It's called a bus, right?
Yeah.
That line.
hmm
Why does it like being in a bus configuration instead of like a star or a circle or a circular or something like that?
I'm actually not really familiar with stars and circle formations, but it's from what I know, they use a bus because every node should be able to access it to send and receive messages on it like equally. I, but I'm not really sure what star and circles do. Yeah.
Cool, cool. Makes sense.
Yeah. Okay.
Oh,
I also had a question, if that's okay.
Yeah.
What do you mean by inverted?
Mhm.
Signal, does that mean like it's in 1 and 0, not 0, 1, or does that work?
Yeah, inverted. So if you're looking at CAN low and it's and you see 0 1 0 1 on CAN high, it would look like 1 0 1 0. It would look
Oh,
like if
okay.
you mirrored it above it.
Okay,
Yeah, I have a diagram later on that shows it.
sure.
So yeah.
Thanks.
And usually when we're doing like debugging or anything, we just look at CAN low because it looks like a normal signal. So, yeah. Okay. Any other questions on this part? Okay. So where is CAN used? CAN is used in a lot of industrial applications. Most of the time, you'll hear about it being used in cars and trucks and large semi trucks and trailers. Also for commercial and industrial machinery, such as like cranes and yeah, anything that's a large vehicle. And also a lot of robotics uses it as well. So like manufacturing lines. It's good for things like yeah, logging and streaming data from cars, heavy duty fleet telematics. So being able to diagnose any problems and gain vehicle data from while and not having to hack into every sensor of the car and yeah, predictive maintenance again using that data. Something I want to talk about is OBD2. Are you guys familiar with what OBD2 is? Has anyone heard of it actually? For us. Okay. OBD2 is a CAN standard. So if you ever take your car to the shop and you see the mechanic plug something into your car to read data from it, that's the OBD2 port, the onboard diagnostics 2. It's I think it was in like 1997 they made it standard on all cars mainly to track emissions data, and then in Canada they took that away sometime in the 2010s, and in electric vehicles they actually don't have most of them. They don't need to have normal OBD2 ports because they don't have emissions. And OBD2 is a form of CAN. It's a higher up layer of CAN, but it is using CAN network inside to access the data.
When you say higher level of CAN, what's that mean? Is there a lower level of CAN or?
Yes. Yeah, that will be in another slide. Yeah, I'll talk about that.
Okay, cool.
Yeah. Oh, and something to point out, OBD2 is an industrial standard. And again, in most cars that are a bit older, you'll see it because they need to be on the same standard. But then in new EVs and things like that, especially Tesla, they don't use the same standards. So they'll use their own encoding system for CAN. So it's a lot harder to diagnose Tesla problems if you don't have a Tesla dongle or if you don't take it to the Tesla store. And why do we use CAN? Three main reasons. First, it's fully centralized. So every node, every ECU is on that as a main network. It's very robust. As I talked about, the electric and electromagnetic disturbances are reduced, and yeah, it's used in large industrial standards that have a lot of disturbances that happen. And finally, it's very efficient. CAN frames are prioritized by ID, and the amount of layering you can have in priorities is quite a lot. Yeah, without any interruptions of other frames. Okay, moving on. Oh, yeah, and quickly, I kind of mentioned this already. So there are three main industrial standards used for CAN right now. First one is SAE J1939. That is more in like heavy duty trucks and buses, large machinery, so not like consumer vehicles. OBD2 is used in, again, normal consumer cars, especially older ones. Newer EVs may not have it. And CAN Open, which is more used for robotics and yeah, manufacturing systems. And that's a bit newer standard. So before I move on to like the CAN frame, was there any other general CAN questions?
Yeah, can I have a question?
Yeah.
Why are there multiple standards and not just like what's the difference between the different standards? Why not just have one?
Mm-hmm. So I'll talk a bit more about that when I talk about the layers, but in general, CAN itself is very basic. It's just a way of transmitting a digital signal. The standards allow companies to work together better at a high level. So then it's a lot about how the message is packaged and transported, and then received and decoded. I think it's just that like when they were developing CAN in the past, it kind of split off into different versions and different standards for different industries. And there wasn't like a consistent one industrial standard of CAN being used. And also like for things like proprietary encoding and decoding systems, they kept it separate. So that people can't just like open up something and hack in easily.
Cool. So it's just dependent on like what data each subset of things needs based on like whatever the standard is.
Mm-hmm. Yeah. It's quite industry dependent mainly, because like a manufacturing line doesn't really care about engine data, for example. Yeah.
So I guess we do OBD2 then? Our standard or our CAN standard is OBD2?
So actually, putting ours into one of the standards is actually really overcomplicated, mainly because the TMS 570 doesn't have the software stack to support it. I would have to write one myself, and I'm not going to do that. That's going to be overkill. On Raspberry Pi, they probably have drivers that support, I'm guessing, CAN Open or J1939. But in order to use that, all of our devices would have to use it. So yeah, we can't do that. Just blame the TMS 570.
Are you familiar with what the difference is between the OBD and the SAE one? Because I keep hearing about the SAE one. I only hear the OBD a couple of times, but they're still controlling like vehicles. It's not like CAN Open, which is controlling like an arm or into some control line. But yeah, Serge loves that one. Yeah, that one Serge loves.
Yeah.
Anyway, yeah, what's the difference between those two? Do you know, like, to me, it's still like both of them are vehicle standards, but I don't know the significant differences between the two.
I'd say it's more about how it's packaged. So, and just, yeah, I guess the way they created it in the past. For example, on the left, it says they'll use like a suspect parameter number, SPN. And on the right, I'm not really sure. But it's just how they chose to package and send information. Yeah. There's probably a lot of differences in between them, but I haven't looked that deep into them yet. Yeah. So moving on to the CAN frame. Before I talk about it, I should get to the OSI model because I think people had a lot of questions about this. And this is when I was talking about layers. So in the traditional OSI model for networks, there are 7 layers: physical, data, network, transport, session, presentation, applications. For us, we only care, for CAN, they mainly care about 3 levels, which is the purple ones. The lowest level is physical, and the physical level always means just your normal digital signal of zeros and ones. We don't care too much about it because the hardware components and transceivers inside of our devices already do that for us. The main part that us on Team Phantom care about is the CAN frame, and this is how the zeros and ones are packaged into transmittable messages instead of just loose zeros and ones. So this will put it together, and I have a picture in the next slide. The standards I talked about, CANopen, J1939, and OBD2, they do a lot more. One example is that at a CAN frame level, you can only send 8 bytes of data at a time. But up here at application level, you can send way more data at once, and it packages it together, and it knows how to encode and decode it properly. So yeah, CAN frame is, again, 8 bytes of data, and when you go up to the application layer, you can do a lot more, and you can do a lot more with the data being sent. I hope that clears it up. Again, we are working at this layer, basically.
Could you explain what OSI is and what layers mean?
Mm-hmm. I forgot what OSI stands for. Anyone know?
In the chat.
Okay. All I remember is OSI is used mainly in computer networking, so things like your internet communications, and this is just a diagram kind of based on that model.
Yeah, I think this applies to any kind of networking thing where you have multiple devices talking to each other.
Yeah.
And yeah, this is like how the internet works, pretty much.
Yeah. Yeah. And in CAN, we only care about these 3 layers.
Why do we only care about those 3 layers?
Oh, that's just how CAN works. CAN only exists on these 3.
Huh?
Yeah, it doesn't follow like the traditional internet model. Like the internet model will use all 7, because some people say that for CAN, the application layer takes care of these 5 layers. So it's kind of all one.
Oh, so those 4 yellow ones don't exist at all?
Yeah, we don't. You don't really care about those.
Oh, okay.
Yeah.
So would it go from physical to data link to application? Okay.
Something like that. This is I'd say more of a representation of where things exist. Yeah.
I can just add on to that quickly that presentations like encryption and that stuff. Session is the different ports in your computer. Transport is how it breaks up the data into small bytes. And network takes care of the addressing of each device on the network and the routing. And so you probably don't need those for CAN.
Okay. I wish MSc offered like communications courses and we actually learn about all this.
Cough, cough. C3.
Yeah, let's go, everyone.
Taking one in
C3, learn
ENSC.
about OSI model. Let's go.
Isn't the internet TCP/IP?
Yeah, for the most part. TCP is the transport layer, and IP is the network layer. And then above that, you have like HTTP in the session layer, and then like encryption protocols and presentation. Yeah. That's like what I Googled after I couldn't answer the question in the interview.
Nice. Yeah. Okay, I'm gonna move on. So the CAN frame. In a CAN frame, we have a lot of things involved. So it starts with the start of frame, and that's 1 bit. These are all in bits. And then we have a identifier. This is the ID number, basically, of usually of the device that's sending it, or the specific component that's transmitting it. This can be 11 to 20 or 28 bits. In this diagram, it's just 11 bits. I'll talk about that more later. And then we have a remote transmission request, control, and then data, again, 0 to 64 bits or up to 8 bytes. Cyclic redundancy check. This is actually, you'll see that in BMS as well, but this is basically CAN will automatically encode everything sent before it into a key of some kind. And then when it's being received, it checks the key and checks the message. And if they don't match up, then they know that something is wrong. So this is just a redundancy check to see if the message is actually intact while it was sent. And that's another part of the redundancy that CAN uses. And then we have acknowledgement and end of frame. I'm going to talk a bit more about some of these components. So again, the important parts for us are identifier and data. The rest of these are automatically done from our TMS 570 drivers and whatever CAN drivers we use. So the identifier, again, has 2 options. These are just 2 different industry standards. So there's the 11-bit option, which is CAN 2.0A, and the 29-bit option, which is CAN 2.0B. And usually the identifiers are per ECU, or again, like per sensor. For example, if you have like a tire pressure monitoring, that would have its own identifier. And it's used for the arbitration process, which is how it sets the priority. Just a side note for Team Phantom, because we only have 3 nodes, we're not going to only have 3 identifiers. Each message type will have its own identifier. For example, if we were sending the average voltage of all the batteries, that would have its own identifier. And if we were sending, critical error needs to shut down, that would have its own identifier. And yeah, I'll talk a bit more about how those work in the next slide. Arbitration. So this is how the priority and which message is determined when everyone's sending. So as I mentioned, every device, or for us, every kind of different message has its own identifier. And the general rule is that the smaller the number, the higher the priority. So if someone's ID was 1, it would be more important than and a higher priority than 2 and 3. And because CAN can send messages at any time, kind of, there needs to be a way of knowing who goes first or who sends it first. And the way I like to put it as an analogy is, let's say there's 3 people standing around a bulletin board, and all 3 of them want to put up their poster. So they would have to kind of fight, or in CAN's case, it's the arbitration phase, to put it up. So person 1, because they're the highest priority, wins, and they get to put up their poster first. And then everyone goes through, and then basically the whole bus is showing the whole CAN frame. And when this is completely finished, then the next 2 people can put up their poster. So person 2 would put up the poster next because they're higher priority than person 3. But once the poster is put up, everyone sees it, and no one can send any messages while it's up there. So no one can just interrupt them halfway through the message. And on the hardware side, that's called the arbitration process, where basically the lowest number is going to win. So for example, here we have 3 nodes and we have the bus. So the bus is going to be the bulletin board, or what's going to be shown. Each node is going to present their number, and if we go one by one, the lowest whoever has zeros first basically will beat out anyone who has a 1. So for example, here they're all the same. On bit number or label 5, node 1 has a 0, node 2 has a 1, and node 3 has a 0. Because node 2 had a 1, it's going to lose because node 1 and 3 have zeros. So if you look at the bus will reflect the 0. And the red line indicates that node 2 has already lost, basically. So now we're looking at node 1 and 3. They're both 1s, so they're the same. And then node 3 goes to 0 while node 1 goes to a 1. And because node 1 is a 1, it's higher, the number is larger, it will lose. So you see it's red here. And the bus will reflect that node 3 here has the 0 and has 1. And then it will just continue on following node 3. So if you were the bus, if you were a 4th or 5th observer and were not trying to send a message, all you'd see is an exact copy of what node 3 was trying to send. And then node 3 goes and sends its data. On a hardware or embedded level, you can think of it basically as a large AND. This thing keeps popping up. So if you AND 3 zeros, it's a 0. If you AND 3 ones, it's a 1. If you AND 0 and 1, you'll get a 0. So 0, 1 is a 0. If you here, if you AND a 0 and a 1, it's still a 0. Okay, questions, go. I'm sure this was confusing.
I have a question.
Yeah.
So does then do node 2 and 1 know that they lost the arbitration?
Yes.
And then do they resend immediately after the message is done, or do they wait till the next cycle or whatever to try and send again?
So yes, they would have to wait until this entire frame is finished. So after data is sent, after CRC and end of frame is done, then they can try again. And then the decision if they want to try again or not is kind of on a driver level. So for TMS 570, you can enable resend transmission if it didn't send the first time. So it would basically keep spamming it until it gets it through.
Okay.
Yeah, so those are just driver settings. Yeah.
Cool.
Are all nodes talking at the same time, or do they like go sequentially?
So the point of arbitration is to kind of choose who wins in that point in time, because nodes it's asynchronous, so nodes don't know when another node is doing something. All they know is, oh, the bus is being used, I can't send anything. And then once it sees that the bus is not being used, it can try to send its identifier to win the arbitration phase.
Sorry, I don't know much. Can you explain what a bus is?
Oh, sorry, no, the bus is just it's just the main CAN line. So I'll go back to the poster example, the bulletin board, right? So if you have 3 people, if there's already a poster on the board, nobody else is going to try to put their poster on the board. And once that poster is taken down, the next 2 people or 3 people can try to fight for the bulletin board again. Did that make sense?
Yeah.
Okay.
You have some questions in the chat there.
Oh, okay. I can't see the chat. Let me check it. Oh my, there was a lot. Where is it this one? Okay. Is 0 recessive bit is one dominant? I don't remember what dominant and recessive bits are, sorry. Gabe.
Should I say it's not okay? What do I say?
Yeah, you can say it's not okay. But you know the answer.
All good. Just keep going.
Oh, okay. Oh, I didn't know I squared C did that too. Pull up resistor, I don't think so. Open drain, I don't know what open drain is. Yikes. I should know these maybe. Gabe, do you know the answer to that?
These are no pull up, but you have those 120 ohms on each end, right? And not open drain either. So it's kind of weird where you have like these things called dominant and recessive bits. So like Xinglu said, the logic levels are sort of weird, where one they go to like 2.5 volts. Do you have that slide still? Yeah, so 1.5 to 2.5 and 2.5 to 3.5. So when can sense, I don't know, that's what I was asking. I don't remember if it's a 1 or a 0. I think I have it backwards. Like when can sends a 1, that's a recessive bit. So can low is at 2.5 volts and can high is at 2.5 volts. And so like there's 0 difference between them. And then when it's dominant, then they split up and can low goes to 1.5 and can high goes to 3.5. So the recessive bit is almost like the point at which each it's almost like letting go of the bus, similar to like open drain in a sense, and your two resistors pull those two lines together, both to 2.5 volts, and sit there. And then when they're driving the bus, can low will drop down to 1.5 and can high up to 2.5, and then they call it a dominant bit. Yeah.
I don't.
If
Are
you
you
just,
saying the resistors pull up the bus?
it's almost like a pull up, but it's like pulled together, like pulled to the middle, because they're
Because they're
connected.
not. It's not connected to power, right?
That's right. Like they're connected to each other. Can low to can high.
Mm.
So
they're
like
connected to each other.
yeah. So like when your ECU lets go of the bus, those two lines almost come together to the same voltage through the resistors.
Yeah, at 1 they come together.
Okay, so it's 1. Yeah, that's 1 is recessive. Here, I'll send a picture in the chat. So then, like Xinglu said, if they all send the exact same 1s and 0s, then we're good. But as soon as someone doesn't send a 0, then they're going to lose the bus because they're basically letting go and letting it go to recessive while someone else is dominating it and sending an actual signal that drives the bus.
So is a 0 here at 2.5?
0 is
I
the
guess because
0
the
is the
diff will be 0.
dominant. 0 is the middle one.
Yeah, 0 is dominant.
It's almost the same idea as open drain, where the dominant is 0 and then you're letting go of the bus for the 1. It's just that in our case, letting go of the bus doesn't pull it up high. The two lines come together. And that's because we're doing a differential pair.
Yeah.
So you can imagine the difference, right? You're always looking at the difference between the signals. Difference between can high and can low is 0 there. And the difference before is different there. Sorry, Xinglu, please go on.
Oh no, that's good. I just forgot what those terms meant, I think. But I never learned open drain, so.
That's fine. Yeah, it's just to explain arbitration, like when someone's dominant and someone's letting go of the bus.
Oh, I thought I had an image of basically that, but I guess I didn't put that in. Yeah. Okay. Yeah, that's arbitration. And quickly, data is digital, represented in hex most of the time when we're receiving it, and we can have up to 8 bytes maximum. If we need more than 8 bytes, then it's an application layer issue. So that's where J1939, OB2, and etc. they come in and package it better so they can send more data at a time, uninterrupted. Okay. So now we're going to talk about how I'm using it, we're using it for our vehicle. Again, our 3 nodes are the VCU, BMS, and dashboard. I'm sure you've seen diagrams like this already, but CAN is going to be this main bus here. And also this should be blue, I guess, but it's going to be here. And if data from any of these needs to be communicated to each other, they'll be sent across. For example, yeah, like average battery voltage or current or what's being drawn from the batteries. Sorry, temperature or what's being drawn from batteries, and the status. So for example, like how does VCU know if the BMS is alive? What if it just died suddenly? So maybe every second or every millisecond it can send a I'm alive signal to the CAN bus, and this could be for um, all three nodes. And that's something I'm working on with the other members, which is understanding what kind of messages need to be sent through CAN, how often, and what their priority needs to be. Right now we have I'd say about 20, and I'm gonna have to put them in a specific order because everyone gets their own priority. So yeah, messages sent are things like battery, device status, battery voltage and temperature, any critical information, and finally any kind of data that's being logged, especially if it needs to be transported to the dashboard.
Could you go back, to that image, the thing?
Okay.
Yeah, sorry. I just question. So like, so that blue line between VCU and BMS master, that's the CAN bus.
Mm-hmm.
But what are those other two lines from going to like charger and dashboard?
Mm-hmm.
Like,
so this line should be blue.
Okay.
It's the same bus, yeah. It was just not drawn like that when we drew it, yeah. This is a special case. Probably Mahmood can answer that better, but when we're charging the vehicle, it's not connected to the main car anymore. So this would be I would say this is a separate CAN bus that goes in another direction when it's disconnected.
Yeah, we're gonna have a
Okay,
specific charging mode for the BMS master because it's not gonna be connected to anything else except the charger and whatever peripherals it has.
So like when the batteries are taken out, then it switches to the charger, not the BMS master.
What do you mean?
Like the blue line, disconnects from BMS master and goes to charger, or
like you can forget about everything else on the left. It would just be the BMS master and the charger.
Okay.
It would just be directly connected to the charger only.
Mm-hmm.
Yeah. This is my last slide. So we use something called a DBC file or a CAN database file. And this is basically an encryption decryption system of what we're trying to send. For example, let's just say that I want to send battery voltage. Through my ID, I should already know that, let's say ID number 20 is battery voltage. So if somebody's receiving ID 20, they're like, okay, this is coming from BMS and it's talking about battery voltage. Later in the way that the data is going to be set up will be predetermined, and every device will be able to know and encode or decode it. For example, if we want the battery voltage to be sent in a few bits, we can set it up in a certain way, and then once, let's say, VCU receives it, it'll know that, oh, I need to multiply by another number in order to kind of decode that message to understand what it's really trying to say. So for example, in this example of, I think this is a J1939 signal actually, but they're able to decode the CAN ID, so they'll know that it's talking about engine speed, and then from the data bytes, it will know, for example, three different values, 621, min, and max. And this way you can send different kinds of data from the same sensor in one message at a time. Hope that made sense. Okay. Yeah, that is all for my CAN presentation. Are there any questions now?
Is the DBC file mostly for testing, or can you make use of it within your microcontroller as well?
Okay. So the file itself is mainly for testing if you're using a PC or some kind of dongle to try to understand, because the purpose of an actual DBC file is if you get a ton of like digital data from CAN, it will process it for you and spit out things like engine speed, RPM. It will give you something like this, or even graphs, so it's really easy to understand as a human. But you can't really like put a DBC file into a TMS 570, for example. I'm gonna have to write some kind of library or system to be able to decode everything that's being sent and encode it as well.
We might need to do that then, right?
Oh, we will be doing it.
Okay, yeah, because
Yeah, there's
That's why I'm.
still. Sorry, go ahead.
Oh no, that's why I've been talking to like Mahmoud and Gabe and Faraz about what all the data types are and what kind of information needs to be carried through. When that's, I think that like everyone knows, they all know what needs to be sent at this point, and then I can put it into a database. And in the future, if I need to add things, I'll just add it into the database. Yeah.
Yeah, it's cool because if we just put all our signals on to CAN, then if you just plug your one CAN dongle from the CAN bus in the car to the PC, then it can like automatically convert all of those messages into straight up like curves of, like if I stomp on the foot pedal, I can see the foot pedal curve going up on my computer and all that stuff. So it's going to be sick for seeing that data.
Yeah, very good to visualize data. Yeah.
And just to add on for dashboard side, I think there's a really nice Python package called CAN-Tools, which parses DBC files and can encode and decode a CAN message. So I haven't used it, but it looks promising.
That's good. Yeah, I'm glad we're using Raspberry Pi and Python because they did a lot of the work for us, and that's going to be like higher layers, higher levels of code. For TMS 570, I have to like tell the CAN, every part of CAN that it exists and what to do with anything that happens. So that's lower level.
Yeah, no, that makes sense. It's very lower level.
Yeah.
Oh, question actually. Do you have anything? Do you have something right now, like that's progress on your project? It's nice to see what it looks like in code this time. How you
in code.
Like how would you plan to apply what you're gonna do? Do you have like something in Code Composer?
In Code Composer, like I have a chart if you wanted to see that, but if you're talking about Code Composer, sure. I had to keep restarting because of new discoveries I made.
Oh.
So it's just a lot of like template code just to try to get things working. And I'm now ready to start integrating things together though. So
what's the chart? Was it? What chart were you talking
about? That's just like the. Let me find it. One second. Oh man, where is this chart? So many folders over here. Engineering controls, documentation. Okay. This is like a diagram of my workflow for CAN.
Are you sharing your screen? Can't see your screen.
You see?
Now I see it. Wow.
Okay. So this is mainly done right now. So I can show that file as well. This is just trying to get all the requirements going. And there probably will be more added on in the future once each component realizes that they need more information. But yeah, this is just like a really quick look at what kind of data needs to be sent, how often, and the sizes. And I can start working with this. I'll probably, at today's meeting, I was gonna do like a last call for this before I put together my first database, my first version of the database. And so these three basically go into making that database and the encoding decoding system. In parallel, I was also basically researching on the data link layer, or the CAN frame basically, for TMS 570. There's a lot of low-level dumb driver things that I had to configure and understand before I could start putting things together. Like if it receives a message, what does it do? Things like that. And then from there I can write the driver for TMS 570 or like the Phantom CAN driver, and then reintegrate it and test.
What's the data link layer? It's not one of the OSI things.
Yeah, it's the
I
CAN
didn't
frame.
quite absorb that. What is that layer supposed to do?
So the data link layer is the CAN frame, so this part.
Ah.
Yeah. So I have to get
the literal ones and
up.
zeros being sent.
Yeah.
Gotcha.
Another thing I've been using a lot is the vector tool for CAN. Okay, I don't have my second monitor, so this might not appear very good. So I can try opening that. Oh boy. This took so long just to get up and going. That was another big pain. Like understanding this hardware, this software for debugging. Because there's no good tutorials on what I want to do. Okay, it's called Canoe. Yeah. I hope my computer doesn't die because I'm not plugged in right now. Can it run it? Okay. Oh yeah, all their things are like CAN something. CanDB, Canoe, Canalizer, Can. What are the other ones? But Canoe's like the weirdest one. Oh, hurry up. What's happening? Okay, full power. Is it? Okay. Oh no, it's not happy with me. So this is like what I've been using to test CAN. And yeah, this part you'd see messages come up. Here is where the DBC integrates into. So if I ran it, right now I just had something called Team Phantom VCU sensor, but I could, if I sent the correct data, I could see values show up. It could refresh every half second or something. This tool actually is really powerful. It can do everything. So analysis, simulation, test. It has its own built-in scope, which is pretty nice, especially if I didn't know if anything was actually turning on. Let me go to the, I forgot which one it's in. Oh boy. Here. Okay, so this is something you can do with Canoe. And basically if I had the CAN system set up and I had some, sensors and, for example, a brake pedal, sorry, not brake, the accelerator pedal, I could have it live decode information and put it into graphs and charts. So this is like a value, for example, it could be voltage. These are just on and off lights to simulate dashboard, for example. This is a switch, I think. I can't tell. Yeah, it's a switch. This is a button. I don't think I can click it because my CAN isn't running. But this is a button I could use. I could have a battery life indicator, a millivolt for something, I guess. Angle sensors, GPS, speed, and coordinates. Not coordinates. We call that coordinal. But yeah, this would be really nice to look at once the whole embedded side of the car is more complete, and then we can just plug it in and read data straight from the. Yes, it is. And there's so much more. This is just some of the things I was playing with.
So how busy do you think our CAN bus will be with all the messages we have?
It's, I mean, comparing it to a normal car, not busy at all. Looking at what we need to send, whoops. It doesn't seem too bad because these are all like 1 byte every half minute. And each signal usually takes, oh, I forgot the time. But it's not very long. I think it's like in like 20 microseconds. Wait, is that right? Okay. But yeah, it's not very long and it's not very crowded.
So should we add more stuff in there?
Yes.
We have.
There's capacity to add a lot more. I'm more worried about the components that are receiving it if they can handle it.
Right.
Yeah. I think that would be the more of the limit.
Someone else needs to go in here and put all the charger commands, right?
Mm-hmm. Yeah, that would be separate because it would be a completely different state. So it would be in a different. I mean, I can add it into the same DBC with no problem. But right now, it's mostly focusing on like vehicle running, and then doing CAN charger later.
Makes sense.
Yes, all the new sensors would go inside of inside here, like the tire pressure, ride height, everything. And we actually, like Team Phantom, we went to a company a few years ago called Mojio, and what they did was they made a dongle that you plugged into your car. It was wireless, it connected through cellular, and you had an app on your phone, and you can read everything about your car live or stored. So, for example, like if you went out for a drive and you come back, you can see, I mean, there's too many things to look at, but like average speed, GPS settings, battery voltages of your car, things like that. And they would stream it to your phone, stored in a server somewhere, I think. Yes, it's a data logger, yeah. But
Wait, what's that called again?
You can access my phone. Sorry?
What was that called?
The company is called Mojio, but I don't think they actually sell it. They just distribute it. They sell it to distributors. So they sell it to other companies to sell it. But it is called Mojio.
Can we get our hands on that?
Well, we wouldn't have any use for it because it's OBD2 standard.
Oh, no.
Yeah, I that's why at one point I wanted to make our car OBD2, but then I also realized if I did take up all the time to put in the stack for firmware, I have no way of decoding it because OBD2 works on, standard things like engine and things that we don't have basically in our car. A lot of different things that we don't have. Yeah.
Does Tesla use it? No, Tesla doesn't use OBD2, do they? Or like Toyota? Do they use OBD2 or?
I'm gonna say no. I'm gonna guess no. Or a variation of OBD2D, probably. It's like a proprietary version because they don't want people to like. For a normal car, you can buy a dongle off the market for like $10 and stick it in your car. You can read everything. That's what I do for my car. But Tesla doesn't have to do it, so they probably don't do it. Otherwise, they would lose customers for mechanics. I mean, yeah.
Yeah, Tesla's super against fixing their cars. Like, they will not let you touch anything. There's been an ongoing battle, especially in the States, with the Right to Repair Act.
Oh, so Tesla is the Apple of cars then.
Yes.
Yeah, yeah, you got
I
it.
did not hear about that Right to Repair Act. I'm like, oh, okay, shit.
Yeah.
What if you worked in Tesla and then you know how to fix it and you can repair it yourself?
You'd have to steal their dongle, I think.
Oh
You
shit.
just the thing is, they use a lot of proprietary parts, and they won't let you buy those parts.
Yeah, exactly.
Oh, that's shit.
So there's this guy on YouTube. Actually, he's pretty much like the Tesla guru. He has a YouTube channel that basically just flips Teslas, buys broken ones, and fixes them up.
Rich Rebuilt.
Yeah,
Yeah,
Heard
Rich
of him?
Rebuild.
yeah, he's pretty cool.
Mm. Okay. Yeah, we're probably gonna move on to our controls meeting soon. So yeah, thank you for listening and having all these great questions.
Thanks for presenting.
all.
I learned
Yeah.
a lot.
Zinglo, I have one more question.
Yes.
If somebody wanted to work on CAN, is there work for them to do?
Yes, on the Raspberry Pi side.
Only on the Raspberry Pi side?
It would just be really hard to do work on TMS side because you need to have everything, and like there's only one dongle for the
Okay.
vector software, and I'm relying on it heavily to do it work because I can't tell what's going on if I don't use it.
Do you think like somebody could work with you and then use your system to test? Or is that hard?
I mean, it's. I mean, I could totally get someone to help me, but then they wouldn't. They would help me on things like, for example, like setting up the hardware, sorry, the database. But for hardware specific things on drivers, it would be really hard because I really need. We really need to use that vector dongle. Otherwise, it's really hard to tell what's going on inside.
Okay.
Yeah. But yeah, Raspberry Pi side, there's a lot because I'm just assuming that I don't need to deal with the driver stuff, and it's a lot easier and more, like just like it is. I'm assuming that the software itself is able to know that the CAN is on, things like that, receive messages, and you just need to put in the database and